How's it going, everyone? Mr. Geyser here with our Lesson B video for the secant, cosecant, and cotangent. For this lesson here, we want to try and challenge you to identify these radian values here in trying to make something that's equivalent to these larger radian values. In example 5, we want to evaluate without using a calculator by using the period of the function and the values of the unit circle. In part A, we're given secant of 13 pi over 3. First, we want to try and take that argument there of 13 pi over 3 radians, and we want to break it up into this sum of two values. Something of the period values for the function of this trig, and the remainder that is equivalent to our initial radian value. One thing we can separate with this 13 pi over 3 is into 12 pi over 3 and 1 pi over 3 radians, which really, that 12 pi over 3 is just 4 pi. Since this is equivalent to 4 pi, what we're really doing in 13 pi over 3 radians is we're rotating around the unit circle twice before landing on that 1 over 3 pi radians. So we can break this down and say that this 13 pi over radians is equivalent to this pi over 3 radians. Now that we know this, let's take a look back at that secant function, where secant is just going to be that ratio of 1 over our y value, 1 over our x value. Once we have that x value there in the denominator, we bring up that unit circle, and we want to try and grab the x value from that coordinate at pi over 3. This is also the x value at the radian coordinate of 13 pi over 3. We're just rotating around this unit circle twice before landing in that position. Once we're grabbed this value here for 1/2 for x, we just plug that into the denominator and find that 1 divided by 1/2 gives us 2. We're now taking a look at B for cosecant, where the argument here is that 17 pi over 4. That first step is to try and bring it out and break it into those two sums. And this 16 pi over 4 really is just equivalent to that 4 pi yet again, plus pi over 4. And we can state that 17 pi over 4 is exactly equal to pi over 4 in terms of our radians. Once we have this here, we now just go to our unit circle, and we're able to grab this y value at pi over 4, which is just the root 2 over 2. We plug that into the denominator, and now we need to use that multiplication trick, where we're multiplying by that radical over itself to remove that root 2 in the denominator so that we have this proper fraction of 2 root 2 over 2 to get our answer of root 2. Now let's take a look at part C. For part C, we now have cotangent. For cotangent, it happens to repeat every pi, so we really just want to break down this argument here of 9 pi over 2 into something that's pi plus that remainder. In this case here, we're able to break it down into 8 pi over 2 plus pi, and we can convert that 8 pi yet again into 4 pi and remove it so we can state that 9 pi over 2 is equivalent to pi over 2. Once we grab that pi over 2 value, we want to try and find the x and y from that specific p point where it happens to be x is 0 and y is 1. Since x, that numerator, is 0, our end result is just going to be 0. One final trick we want to take a look at are these negative arguments. When we have secant negative 17 pi over 6, what we can do is separate it into this difference. We now have negative 12 pi over 6 minus 5 pi over 6. We're just separating it again, trying to convert that negative 12 pi over 6 some value to get a proper unit of around the unit circle, 1 rotation. And now we're saying that negative 17 pi over 6 is equal to negative 5 pi over 6. But negative radian values are difficult to use. So we can convert this negative radian value into its positive equivalent. What I mean to say is, if we start at the unit circle here, and we go back negative 5 pi over 6, it's going to land up in the same position as though we went the proper counterclockwise way, 7 pi over 6. Now to determine these equivalences here, there's no easy way to do it. One way you can try is just by adding 2 pi to this value to get this proper value here. Or if you're given a unit circle, just find where that radian ray is. Now that we know that we're dealing with 7 pi over 6, That's the radian value we want to try and find. Specifically, we're looking at secant, so it's going to be 1 over x still. That x value at that 7 pi over 6 and that negative 5 pi over 6 is going to be negative 3 over 2. We plug that into our denominator. We still need to use that trick of converting that root 3 in the denominator into the numerator up here by multiplying its equivalent 1 value. 1 value being the radian value, or radian 3 over radian 3. We then end up with negative 2 radian 3 over 3 as our final answer. For this next part, we want to look back at the ratios from example 1. Can you name the reciprocal identities and the quotient identities in terms of trigonometric functions? For this here, we have 3 reciprocal identities, where we're just trying to find the reciprocal equivalent of cosecant, secant, and cotangent. And we know that cosecant refers to sine, secant refers to cosine, and cotangent refers to tangent. And we find that the reciprocal versions of these trig functions is just 1 over that reciprocal trig function. Now we have 3 different reciprocal identities and 2 quotient identities. The quotient identities deal with 2 trigonometric functions, where cotangent happens to share a quotient identity as well as a reciprocal identity. We know that tangent is that y over x, and we know that cotangent is that x over y. And in terms of our trigonometric functions for radian values, it's going to be sine over cosine and cosine over sine. Finally, when we find these exact values given by these terminal points here, we want to try and find an angle that's rotated in this coordinate plane. You should create a right angle triangle by dropping a perpendicular line back to the x-axis and use the Pythagorean theorem to find that hypotenuse. Let's practice that now in our next examples. For example 6, we're going to find the exact values of each of the 6 trigonometric functions of an angle theta if we're given this value of negative 2, 5 is the point on the terminal side. Well, that first step there is to create that trig triangle where negative 2 is going to be that x value at the bottom, while 5 is going to be the y value that creates that red side. Then we can find that hypotenuse of that right angle triangle there by just plugging in the square root of x squared plus y squared, and we end up getting that root 29. Once we have that there, we're basically done with our calculations. All we need to do is plug and chug out these 6 values for the 6 trigonometric functions. For these 6 ratios here, all we want to try and create is that we want to plug in each of these y, x, and hypotenuse values into these 6 fractions. As a reminder, we don't want to try and have those root 29s inside of the numerator, so we can multiply by root 29 over itself twice for our sine and cosine of theta values to get this 5 root 29 over 29, negative 2 root 29 over 29. Let's try this one more time with example 7. In example 7, if we're given sine of theta is equaling 2 root 13 over 13 and cosine of theta of 3 root 13 over 13, we're going to find the exact values of the 4 remaining trigonometric functions of theta using these identities. Well, first, instead of creating that trig triangle, we're actually already given these x, y, and hypotenuse values from our sine and cosine theta. If we look at these ratios here, we can extract this y value of 2 root 13, the x value of 3 root 13, and that hypotenuse of 13. Now we could plot it onto a trig triangle here. If we were just given x or y, we could eventually solve out for that 13. But now, this final step is just to plug in these 3 values into our 4 remaining trig problems. For these 4 values here, taking a look at tangent first, it's just that y over x. When we're plugging in y over x, we're just plugging in 2 root 13 over 3 root 13, and eventually those root symbols happen to cancel out. For cotangent of theta, notice that we really are just taking that 2 over 3, and we're just flipping it to get that reciprocal value. If we take one final look here at cosecant and secant here, we just want to try and observe that since we have this root 13 in the denominator for both of these fractions, we're multiplying by that one equivalency, where it's root 13 over itself, which equals 1. You multiply that 1 to these fractions here, and eventually we get root 13 over 2 for our cosecant function, and root 13 over 3 for our secant function. Now, for example 8, we want to try and work backwards from these graphs into finding not just one, but two equivalent equations. For example 8, if we're given the graphs below, we want to use the suggested functions to write equivalent equations. In part A, we want to write two different equations using cosecant and secant. For that first equation here, we can observe that the skeleton or the ghost equation on this graph here looks like this periodic wave here, where our amplitudes are at these points and at the vertical asymptotes would be these intercept points. For this line here, we can see that it's equivalent to negative cosine x. And we know, going from these trig functions, the reciprocal equation is just replacing this cosine into this secant. Notice everything else is exactly the same. We have a negative cosine of x is equivalent to this negative secant of x. For this here, it's creating the skeleton for this reciprocal function. So this negative cosine of x isn't explicitly this black parabolic function that's flip-flopping. It is specifically this y equals negative secant x. The skeleton, the dotted line here, this dotted line graph is negative cosine of x. But I know you smart students have observed that these periodic functions are just phase shifted between cosine and sine. So what we can really do is convert this cosine of x, this negative cosine of x, into this equation where it's sine of x minus pi over 2. And I'm really just grabbing this equation by observing that if I wanted to find the equation for this function in terms of sine, I would want to try and start at that first key point of an intercept that leads to a maximum. I can find that point right here with a phase shift of negative pi over 2. So I can write this as sine x minus pi over 2. And from there, this is the skeleton for the graph of secant x minus pi over 2. What I want you to observe is that the c value between these reciprocals remain the same. The amplitudes between these reciprocals here remain the same. The negative value in front of our trig functions remain the same. When we're going back and forth between these reciprocal functions, the skeletons a, b, and c and d values persist in the reciprocal function. If we take a look at part B here, we want to write two different equations using cotangent and tangent. We can first observe this here as a negative tangent function. We know that tangent always has a monotonic behavior where it's always increasing. Since these waves here are always decreasing, we know that's just going to be a negative tangent function. Since we do have this little bit of phase shift where that first key point for our tangent function occurs at the 0, 0, we can see that the phase shift is just this negative pi over 4 shifting to the right. We can add that into our c value here, but notice the difference. This equation is this black line here. These black lines here are also the exact equation of positive cotangent x plus pi over 4. Now, you might observe a pattern between this negative pi over 4 and this positive pi over 4. It's not the values that happen to be flipped, rather it's this negative and this positive. If we were to shift this tangent graph a little further to the right, this would become like negative pi over 3 or negative pi over 2. This value here would become plus pi over 6 or plus 0. So this value is shrinking in size as this value increases in size. But it's not that correlation that I want to point out. It's simply that when we have a negative tangent with a negative or positive c value, the negative or positive c value flips when we have this also correlation of this negative tangent flipping to this positive cotangent. For this pattern here, we can rewrite any of these wave functions as this negative tangent or this positive cotangent, in the exact same way that we can write these cosecant or secant graphs in this negative secant of x graph or this positive cosecant of x plus pi over 2. These two equations are equivalent. These two equations are equivalent. These two equations are reciprocals. These two equations are reciprocals. And finally, these two skeleton equations are equivalent as well. Let's take one final look at our last two examples here. For example 9, we want to try and use the identity values of a, b, c, and d to determine what the values are for this trig function here. For our trig function, we're given 2 cosecant of x minus pi over 2. So we can grab that a value of 2, that b value of 1, that c value of negative pi over 2, and since there's no value here for d, d is equivalent to 0. Our next step in graphing these these trig functions here, such as cosecant and secant, is to first find what's called the start point. The start point for cosecant and secant is usually at 0, 0, but since we have a c value, we're going to shift our start point from 0, 0 over to pi over 2. Now that we know what where our start point is, we want to try and find the end point over here by observing the b value gives us the period. Once we have this period here, we can add our period to our start point to find the window where a full length of a wave will form for this cosecant. Our next step here is to create those 4 subintervals based on the reciprocal trig function of cosecant. The reciprocal trig function for cosecant happens to be sine, and we know that those subintervals are going to go from the intercept maximum, intercept minimum, to another intercept here, where really that first and final intercept is just that start value, and that final value, that's 2 pi away. We now want to try and find the middle point between these intercepts here and graph that point now. Once we have this center point, we're able to find the middle of these two intercepts to find the amplitude, that maximum, and the middle of these 2 points to find the minimum. Once we have these 5 key points plotted, we can either choose to create the skeleton equation of 2 sine of x minus pi over 2, or we can go right off the bat and graph this as these cosecant functions. These are just the points for those maximum and minimum values. Now we can graph these vertical asymptotes when it crosses its midline at 0. Now that we have these windows of availability, or these windows of domain for this cosecant function, we now just graph our first 2 parabolas. Now that we have our first 2 parabolas here, we just want to extend all of this information for the rest of the graph. So first, let's plot the rest of these vertical asymptotes here. Once we plot the rest of these vertical asymptotes, we kind of just want to follow along with plotting these maximum and minimum values in this flip-flopping way. And once we find these maximum and minimum values, we just add in those rest of our periodic functions here. Once we have this here, we are finished with graphing these types of trig functions. And as a reminder, if we had wanted to graph that skeleton function, that reciprocal equation was just going to be equal to y equals 2 sine of x minus pi over 2. This little dotted line right here. Now, for the final example of today's lesson, we're given this secant equation in this transformation method. Notice for this first equation here, we're given y equals negative secant of 2x minus pi minus 1. From this position here, we want to notice it isn't in standard notation for us to grab that a, b, c, and d value. We want to try and undistribute this coefficient in front of x if we happen to have a c value that is not closed off by a second set of parentheses. To do this, we're just dividing this coefficient from both of those terms within that argument. So 2x divided by 2 gives us x. Negative pi divided by 2 is just negative pi over 2. Now that we have this standard notation written, it's now really easy for us to grab that a, b, c, and this d value, where the d value is going to determine the midline that we're going to start our equation off with. Once we have this midline here, we now want to use this line here to help us identify where that start point is. That start point comes from the C value. And in this first notation here, we really can't find that C value. So we need to undistribute that coefficient if it happens to be not in standard notation. In this standard notation here, we're able to find that C is yet again negative pi over 2, and we can know that we're going to start at this plane, somewhere along this line here. We don't necessarily know if it's going to be a vertical asymptote or a start point yet, but we know our first key point is going to start here. Next, we want to try and find what our period is. That b value is still that coefficient in front of x, which happens to be 2. So since b is equal to 2, we plug it into that denominator for that period equation of 2 pi over b and find that the period is equal to pi. As a reminder, from these trig functions here, we can automatically write the reciprocal function by simply replacing this secant value here with cosecant, these corresponding trig functions today. For this cosine here, we know cosine has these 5 key values where it's going to start at a maximum, intercept minimum, intercept maximum. Now notice, I didn't read the board correctly because for these 5 key points, it's going to be based on the negative coefficient in front of our secant. Since we have a negative trig function, we're given this as a minimum value instead of a max. We're given this middle point as a maximum value instead of a min, and this final point here as a minimum value instead of a max. Once we have these points, we now go to our start value, and now we plot that first minimum value here. Once we have that first minimum value, we now want to take our period length and go to the next end point here. In this case, it's another minimum, not an intercept like that last equation. So we just go a full pi length over and plot that next minimum point. Now between these 2 points, we want to find the middle, and now we want to plot that maximum value. For that maximum value, we now use that maximum value to find the middle to plot these 2 intercepts. Now that we're given these 5 key values, if you want, you are allowed to graph the skeleton equation based off of those 5 key points, as if you were normally graphing this negative cosine function. But if you do graph this skeleton value, just like this across the whole way, it does make it easier to find all of these vertical asymptotes at the same time based on those intercepts, and it makes it easier to find all of these parabolas based off of the maximum and minimum values. Thank you very much for joining me for Lesson B today. If you have any questions at all, please leave them in the comments down below. I look forward to seeing all of you guys in class. Take care.